Yes, thank you very much. I hope everybody can hear me. Otherwise, I guess someone will interrupt me. I want to talk about ensemble methods for robust support vector machines. And what I want to consider here are binary classification problems. So we have a labeled training data here. Each data point is an n-dimensional vector and has label -1 or 1. And we want to fit a prediction function which predicts the right label for each point in a certain data space. And one very efficient and somehow easy approach is our support vector machines. So what you're doing here basically is you try to find a linear hyperplane which separates the data by its class. I don't want to go in detail here. Basically what you predict then is just the sign of each point when you apply it to the hyperplane. So you just check on which side of the hyperplane the point lies. You have linear programming formulation here. So from point of view of an optimizer, this is nice. But the main point I want to talk about are now adversarial attacks. So what is an adversarial attack? Formally, this is a perturbation of your data point. So you try to perturb your data point in a mostly small ball of radius r, such that your model predicts a different label than the true one. And this can, so you can consider different norms here. So depending on the norm, this can be a different set how for your perturbations around your data point x. And now the question is, how do you protect against these adversarial attacks? Or in general, more general, how do you protect against uncertainty in the data, since these balls around your data point can also be interpreted as uncertain perturbations of your data point. And in robust machine learning, you normally take an uncertainty set. So you define a ball of radius r, and what you solve then is instead of minimizing your empirical loss, you minimize the worst empirical loss about overall perturbations in your uncertainty set U. So this is a classical approach. It was already used for support vector machines. Now in my work here, I want to improve this approach by proposing a robust ensemble method for SVMs. And the algorithm here works as following. So I want to calculate k hyperplanes, so k SVM solutions in the end. So I have k iterations, and each iteration is very simple. So we attack each data point in our data set by an adversarial problem. So we get one adversarial attack here for each data point. Then we solve a classical SVM on this perturbed version of the training set. And here we put higher weights on the points which are not correctly classified by our current ensemble we know up to now, or up to this iteration. And then in the end, we get k calculated hyperplanes, and we perform a majority vote for the prediction. So we just check the labels for each hyperplane, and the majority wins. So we predict the label which most of the hyperplanes predict. So geometrically, what happens, let's assume we have a red class and a blue class. So what we do first is we calculate a classical hyperplane by solving an SVM. Then we perturb our each data point. So we try to fool the hyperplane. We try to put each point on the other side of the hyperplane if it was correctly classified. Otherwise, we can keep it. So now we have a perturbed set of our training data. And now for this set, we again solve an SVM. So we get a different hyperplane now. Now we go back to our original data set. And again, we perturb each point. Now the perturbation can be different, since we don't want to fool only one hyperplane here, but we want to fool two hyperplanes. So the perturbation can be different. We have again a perturbed set. For this, we calculate the third hyperplane, and so on and so on. This is a very basic idea. Now, the big question is, how do we solve this adversarial problem? So I define this adversarial problem here as follows. So assume we are in iteration T. That means we have T hyperplanes already. now we try to find a perturbation which maximizes the number of fooled hyperplanes. So we try to find a perturbation such that the point gets on the other side of the most hyperplanes possible. And you can model this problem as a mixed integer linear problem. So basically here we are, one variable is the perturbation delta we are looking for. And we have variables z, which are 0 or 1. And basically you can check here this left, on the left-hand side, this term is negative if the point is not correctly classified. So if the sign of this hyperplane is different to the sign of the label, then this is negative. And in this case, we can set our variable to 0. And since we minimize here over our z variables, this by this we achieve, we maximize the number of fooled hyperplanes. So this is a difficult problem. We have big M constraints here. We have 0, 1 variables. So what I propose additionally, or as an alternative, is to solve this adversarial problem heuristically. In this case, what I do is very easy idea. I just, the perturbation I choose is just a weighted average of the normal vectors of my hyperplanes. And I give more weight to a normal vector if the point is more far away from the hyperplane. So in this case, I have an average of W1 and W2, and W2 gets more weight here in this average since I'm more far away from this hyperplane, and it's harder to fool this hyperplane, so I have to get more into this direction. This is the basic idea. And so I tested all both ideas and compared it to the classical robust approach. So let me tell you what you see here. So this is the classical robust approach. I didn't show you. This is well known. So this is the ensemble method with the exact adversarial. This is the ensemble method with the heuristic adversarial. And what you see here, the numbers, is the absolute accuracy improvement compared to a non-robust ensemble SVM. So basically, as a benchmark, I'm using a non-robust boosting method. And the difference here is the difference in accuracy. So you want to have a positive value here. I hope you can read somehow the values. So the blue, getting to blue is a better value, and here dark brown is not so good value, is a negative one. So here, and now you see on the x-axis, you see the defense level. So how large is my uncertainty set? When I train my model, I can choose how large my radius is, so I can protect against. If I choose a larger uncertainty set, then I have a stronger protection. So here from 0 to 0.5, I have the defense level, and here you see from 0 to 2 the attack level. So after training, I test each method on a testing set, and I attack each point in the testing set by an worst case attack, and the size of the attack is given here on the y-axis. So what you want, is basically everything in blue, but you see there's always a trade-off. So for small attacks, here the all methods are not much better than the classical non-robust method, but you see that for larger attacks, here the classical robust approach doesn't work well, while the exact ensemble method works much better. And interestingly, the heuristic method is even better than the exact one. And you see that the values also are more constantly better. So here, the defense level doesn't influence much the result, while here you have to choose your defense level very carefully. By the way, this is the digits data set. So it's a small version of the MNIST data set. Yes, to summarize, so this is I presented an iterative calculation for SVM solutions. So there's an exact and a heuristic version, and it seems that the heuristic version can be better. I didn't show you all results. There are also data sets where it's not so clear. But in general, the behavior is much more stable for the defense levels, and also computationally more demanding than the classical method. And if you want to see more you can check my preprint, which is already online. Thank you very much.
Thank you. As you do mention, so your heuristic gets better result than the exact. Is that because there's a timeout on the exact? I'm not sure why.
I mean, it's not so clear. So it's a generalization effect. So you all, I mean, normally in machine learning have this. So, I mean, if you find the global optimum, it doesn't mean that your generalization is better.
Okay.
So maybe it's some effect like this here, so that the heuristic version is better. But yeah, I cannot tell you theoretically, or I cannot explain it theoretically. So I don't have a generalization. Yeah, I cannot estimate the generalization.
Okay, let's see. Anything else? No. Thank you again.